Welcome, rookie. Grab a coffee, pull up a chair, and settle in, because today we are opening up a brand new investigation. In this explainer, we're going to use the correct code framework to solve a classic mystery. We call it the find target element problem. Now, if you're a complete beginner to coding, you might be tempted to just start mashing away at your keyboard, kind of hoping you stumble upon the right answer. But, well, we don't work like that here. We're going to approach this like seasoned investigators solving a case for the very first time. No guessing, we rely on strict logic, clear rules, and absolute proof. Let's get to work.
Real detectives don't rely on trial and error, right? They follow a predictable, step-by-step protocol before they ever hit the streets. So, our agenda today takes us through 5 phases: opening the case file, analyzing the problem space, mapping the evidence board, executing the scan, and finally, closing the case.
All right, let's kick things off with phase 1, opening the case file and defining the motive.
So let's look at the exact parameters headquarters handed us. In our line of work, the motive is called the invariant. You can think of the invariant as this absolute, totally non-negotiable rule that determines if the suspect we're looking at is actually the culprit we want. In programming terms, it looks like this: candidate strictly equals target. All that means is we're asking one very simple question. Does the person standing right in front of us exactly match the description of the person we want? If it's not a perfect match, they aren't our culprit. There's no gray area here, it's just a simple yes or no.
And for this specific case file, headquarters gave us a very clear single suspect to track down. We are looking for the number 7. That's our target. If a candidate isn't the number 7, they're free to go.
Moving right along to phase 2, analyzing the problem space and setting the scene. Before we just start kicking down doors, we really need to analyze our environment. Our problem space here is defined by 4 key facts. First, our input is an array of integers. Just think of an array as a police lineup. Second, our candidates are each individual element or person standing in that lineup. Third, the structure is an indexed sequence, which is just a fancy way of saying everyone is standing on a specific numbered spot, starting from position 0. But that fourth point? That is the most critical. The status is an unsorted array. This means there's 0 logical order to how these suspects are lined up. They're not ordered by height, age, or value. Because it's completely chaotic, our culprit could be hiding literally anywhere.
Take a look at this. Here is our literal lineup of suspects. 5 individuals completely out of order: 4, 2, 7, 11, and 15. We know one of them is our target, but because they're jumbled up, we can't just magically guess where the number 7 is standing. We have to be methodical about this.
Now, because the lineup is unsorted, our protocol dictates the exact tools we're allowed to use. We can't skip around. We have to use a linear scan, which just means we start at the very beginning of the line and check every single person one by one until we hit our target. That's our route. Furthermore, our scope is a single candidate evaluation. We're only interrogating one suspect at a time. We pull one person forward, ask if they are the number 7, and if they aren't, we move to the exact next person in line.
Okay, phase 3. The evidence board and proof layer validation.
Now, this is where the real detective work happens. Before we write any actual code, we validate our logic completely on the evidence board. We prove our case on paper first. Look at how we carefully log the index. That's the numbered position in the lineup, right? Starting at 0. Then we log the candidate standing in that spot. Then we apply our invariant rule. Does this candidate exactly equal our target of 7? And finally, the result. At index 0, candidate 4 is an invalid match. Index 1, candidate 2, invalid. But at index 2, candidate 7 is a valid match. By mapping this out first, we completely prevent ourselves from making a false arrest or getting all tangled up in code later. We already know the absolute truth.
Step 4, executing the scan. It's time for the interrogation phase.
As an investigator, you never, ever deviate from standard operating procedure. We follow a strictly defined process map that runs in a loop. Step 1, select the candidate at the current index. Step 2, compare them to our target. Step 3, ask, is a match found based on our invariant rule? Step 4, if yes, we immediately return the index, the location of the arrest, and close the case. If no, we release the suspect and continue the scan to the next spot. Let's test this out. Let's run the interrogation. Frame 1, we look at the very first spot in line, index 0. We pull in the suspect standing there, candidate 4. We compare them against our target of 7. They don't match. The invariant proves false. So we log the dead end and the scan continues.
We step forward to frame 2. Next spot in line, index 1. The suspect standing here is candidate 2. Check the invariant. Does 2 equal 7? No way. Another dead end. Now, it can be frustrating, but as professionals, we stay totally disciplined. Follow the process, move to the next spot.
Boom. Frame 3. We're looking at index 2, and the suspect standing here is candidate 7. We check our rule. Does candidate 7 exactly match our target of 7? Yes, the invariant is true. We have a confirmed match. We've successfully apprehended our target, so we immediately return the location of the arrest, which is index 2. The interrogation is over. Finally, phase 5, closing the case and filing the paperwork.
Listen closely here, rookie, because this is where so many beginners get incredibly confused. The real detective work, the logic, the proof, the step-by-step reasoning, it's already done. Code is literally just transcription. It's just taking that rock-solid proof from our evidence board and translating it into whatever specific language the precinct demands that day. Whether you translate your findings into JavaScript, Python, or C#, the underlying investigation logic you just proved is identical. You still use a linear scan, you still check that exact same invariant rule, and you still return the index when you find the match. Seriously, don't let the syntax scare you. It's just the final paperwork.
As part of our final report, we got to submit our performance analytics. In computer science, we measure how fast and how efficient our investigation was, using time complexity and space complexity. Our time complexity here is O of n. To put that into perspective, think of O of n, time, like walking down a long, dark hotel hallway where you have to check every single door sequentially to find a specific room. The longer the hallway, the longer it takes. Now, our space complexity is O of 1. This means our memory usage is constant. Imagine you're just carrying a tiny pocket notepad to record the suspect you're currently talking to. You don't need a massive filing cabinet, just one page to hold one suspect at a time. It's incredibly efficient. And why does this matter? Well, when you build real applications, saving memory and time is exactly what keeps your software from freezing up on the user.
So the absolutely crucial takeaway from this explainer is this quote right here. The invariant determines qualification before execution begins. Execution only verifies the proof. By using the correct code framework, we didn't guess. We didn't just throw code at the screen and hit run to see what happened. We established a clear rule, we mapped the chaotic problem space, and we proved our logic on the evidence board before we filed a single line of paperwork. When you plan your logic flawlessly on the evidence board, the actual code is just a formality. You've closed the case. So the only question left is, are you ready to crack the next mystery?